All right, so let's see. All right. So diving into digital forensics is the process of storing, analyzing, retrieving, and preserving electronic data for investigation. Investigation is essentially the biggest aspect of digital forensics, and we'll be talking a little bit more of that below. In terms of electronic data, this could be either hard drives and computers, phones, smart appliances, vehicles, and honestly anything you could find electronics in or data in. Um, More formally, it's the application of computer science to investigate digital evidence for legal purposes. There are generally two types of investigations, public and private. For public, this would include crime or civil investigation and is usually carried out by law enforcement agencies or the government. For private sectors, this encapsulates corporate policy violations or e either like a private investigator or like an in-house or outsourced investigation. So you have public and their private there. And to quote, whether investigating a crime or corporate policy violation, part of the evidence is related to digital devices and digital media. And then this is where digital forensics comes to play and tries to establish what exactly happened. So in one way or another, you're kind of playing detective with the digital information that you have and trying to scope out what really happened or what a user did in relation to an electronic device. To keep going forward, I know we said other examples in the beginning with phones, but this could really be anything, especially cameras, music players, smartphones. And the digital media could include either CDs, DVDs, USB flash drives, and other types of external storage. And so when you're having an investigation for using digital forensics, some common questions you're really going to try and tackle is how should the police or the digital forensics investigators or organization collect these pieces of digital evidence when you have these hard drives and these phones? What is the proper method of collecting these? And what are the procedures to follow if these devices are still running, if they're still live? How are you gonna handle that? What are you gonna do? How do you transfer this digital evidence? Are there specific practices you're gonna use? How do you analyze these collected evidence? And with the transferring of digital evidence and collection, you want to make sure that whatever you do to the device, you're not changing any data. Um, these, if a device was used in a crime or some kind of that promotes an investigation, you want to make sure you don't tamper with these devices. And so, how exactly are you going to do that? That's what digital forensics is here to solve. Um, the last question here, how can we analyze personal devices and storage ranges between tens of gigabytes to several terabytes? Um, Depending on what device it is, we could have a lot of data involved. How are we going to sort through these pieces of data and find exactly what we need? All right, so just to jot over some different types of digital forensics. First, we have computer forensics, which is digital evidence gained from laptops, computers, storage media, um, and so on. As the name says, computer forensics. We also have mobile device forensics, which you might tell is revolves around small electronic devices, digital assistants, tablets, SIM cards, gaming consoles, stuff like that. Next, we have network forensics. So this is going to be digital forensics on networks and obtaining data and monitoring data during either cyber network activities, such as attacks, breaches, or other collapses that may have been caused by malicious software. It also includes abnormal network traffic as well. So forensics with anything dealing with the network. Digital image forensics is the extraction and analysis of digital images to verify authenticity, metadata, and determine the history and information surrounding certain pieces of information. I will talk a bit more about digital images soon and how they work. Next, we have digital video / audio forensics, which is the audio visual evidence to determine, same thing as before, determine authenticity or other information that you can extract, such as the location and time intervals that could be found in like metadata, for example. And finally, we have memory forensics, which is generally the recovery of information running on a computer's RAM and is also called live acquisition. For RAM, for those of you that don't know, when a device is not currently active, the RAM is basically empty and doesn't have any data that's relevant. So in terms of memory forensics, we want to be able to kind of take a picture of that RAM before the device is basically turned on because RAM is volatile. Okay, so moving on to the steps, there's a lot of different steps that you can take with forensics, but they generally follow the same idea. So for this example, we have four main steps here. The images on the right aren't necessarily correlated to these steps listed. So first you have acquiring the evidence, collecting all the digital devices that may be involved in an investigation. Next is establishing a chain of custody, which is something you hear a lot. And the purpose of this is to ensure that only authorized investigators have access with the evidence and that no one that's not unauthorized has the opportunity to tamper with it. Next is placing the evidence in a secure container. That way you don't damage any of the evidence that's being used. And then finally, you transport the evidence and you relocate them to either a digital forensics lab or operations center. From there, you would retrieve the device, create a forensic copy, and then analyze the copy instead of the actual device. And then you could return the device in a secure container, and you could start the processing for the copy on the device. Okay. For the pictures on the right here, we also have some similar steps. We have investigation, collection, preservation, analysis, and reporting. Just like with a lot of cybersecurity related topics, reporting is obviously going to be the biggest aspect or the most impactful aspect. A lot of this, everything you do kind of proceeds to report to your report and your findings and what you're able to figure out. And especially since we're dealing with criminal related activities, oftentimes as a digital forensic analyst, you would have to show up to a court or judicial setting to be able to testify and for what you found on these digital devices. Okay. So yeah, the bottom we also have collection, examination, analysis, and reporting, but you generally get the same steps where you're getting the devices, securing them in a place that isn't going to get tampered with, creating a copy and analyzing that copy, and then reporting it afterwards. Same thing here. This one just has the picture's a little blurry, but a whole bunch of steps. That also includes either returning the evidence, what happens afterwards, or even just a continuous loop of analyzing and then examining the information that you have. Okay. Same thing here. I wrote a lot of steps. Okay, so going into more of the specifics on forensics and some common things that you will see, we're going to drop into file formats. So file signatures are certain leading bytes, which allows programs to parse data in a consistent manner. This is useful because certain files aren't necessarily going to have a file extension at the end of their name. Especially if you're using something like Linux. The file signatures or file magic numbers are bytes that help identify the format of the file, and they're generally 2 to 4 bytes long and can be found in the beginning. In the image on the right here, you can see the first column is a whole bunch of hexadecimals, and those represent the file signatures. And on the fourth column, I don't know if you can see it very clearly, that there's a whole bunch of listed types of file extensions, such as JPEG or I don't know, this one says BPG, but I just took this image up of Wikipedia, but there's a whole list of different file signatures and what they actually map to. And you'll be able to use that as sort of a guide. So as mentioned, files can sometimes come without an extension or maybe even incorrect ones. So using file signatures to analyze and identify the file of the format of the actual file you have is really helpful. Programs don't need to know the file type in order to open it properly, but yeah, it's just going to be really useful in forensics analysis. Okay. All right, so oops. All right, so next is metadata. Metadata is really common and refers to any additional hidden data, which can be used to, I guess, describe the context of a file's actual data. You could think of it as any additional information relevant to how or when the file was perceived or created. So basically, it's data about the data. It could include camera location, dates, GPS location, comments. Especially with, I think, cameras, it even says like what camera it was taken on, and sometimes like the owner of the photo as well. You could get a lot of in-depth information out of just metadata. Uh, Exit tool is, I think, let's see. Let's bring data from size. So yeah. This is metadata for input. So exit tool is like a tool that also displays metadata for an input file. If you I think on the left image here, you could run exit tool and then the file name, and then you could get a whole bunch of metadata tools. So that's a really good console tool to use. And again, we could get different dates from metadata, and which also includes timestamps and MAC events, which stand for modification, access, and creation. So if you modify a file, the time at which that file is modified is also listed in the metadata. So yeah, with metadata, you could create a timeline for when things happened, especially if you have like real life footage that was taken over a period of time. You could use the metadata to kind of map it out and also kind of determine what happened. Okay, so next is steganography. This might be familiar with a lot of folks, but essentially it's the practice of hiding data in plain sight, such as in images or audio. When you see the image or listen to the audio, that looks pretty plain and straightforward, but inside there's actually alterations in how the data is encoded that reveals a hidden message, for example. So LSB steganography stands for um, I think it stands for last significant bit, where you're changing the last bit that of a piece of data that doesn't change the actual data in the bigger picture, but inside it, there's a lot of information that could be taken. So on the image on the right, we have two colors. They're both essentially white, but the last bit is one bit off. We have F versus E. And so 16, 15, it's going to give you the same color, at least to the human eye, but that change in data could be used to hold different pieces, different messages, or different pieces of data. And this could either hide or embed payloads. Sorry, actually. Yeah, so it basically uses to hide data. It relies on several pieces, which includes payloads, carriers, channels, packages, and then the key. So with the payload is your payload, you're asking what are you trying to embed or hide. Carriers are the type of file or asset that hides the payload. Channels refer to what kind of carrier you use. The package is how the carrier looks or responds, and how it's buried with the payload. And the key is how you decode or decipher the message to be able to find the payload. StegHide is a common tool to be able to kind of filter out a piece of data in steganography. So it's used a lot when trying to decipher that. Okay. So next is disk imaging. Disk imaging is pretty simple. You're getting an electronic copy of the device, whether it's a hard drive or a USB, and making sure that you're using the copy to do your analysis and investigations instead of the actual piece of evidence. Okay. In more technical terms, it's a bit by bit or bitstream file that's an exact unaltered copy of the media. One important aspect of, or one important piece of, I guess, data in imaging in general is called a checksum. A checksum is a hash that represents the file itself, and if that file is altered or is even set, if it's different than the original file, the two files will have different checksums. The hash is a good way for catching alterations to the original source, and it's just really useful to ensure that you're getting an exact copy of what you originally have. MD5 sum and SHA-256 sum are commands to get the file checksum, and you also use write blockers to prevent unauthorized writes to the image you're copying from. Sorry, I got distracted. When you're trying to make a copy of a piece of digital evidence. Ooh, that's really cool, Matt. Yeah, Matt posted a link to a steganography tool that he made. That's pretty sick. We'll check it out after. Okay. So next, I think this is maybe one of the last ones we have left. So memory forensics, again, deals with volatile RAM. So the information that can be found on RAM and memory dumps is pretty valuable. And this could be the amounts of data. It's really fun to make. So the amount of data that are found in these memory dumps are really large, but you can use different tools like volatility to be able to siphon through them and then find what you need. And these tools will really help you because the memory is volatile. So with volatility, ooh, that's pretty cool. With volatility, you could run strings for clues. You can identify image profile and to determine the operating system or what version it is. You could dump processes and look for suspicious processes and find anything related to what processes were running on the device. And finally, you could also view data in different formats as well. Yeah. See. And finally, you could process these memory dumps to either store them to a text file if you need them for logging sense. Okay. So last couple ones. We'll also be talking about hex editors. I believe I'll be going over hex editors more this Friday, if you're interested. We also did a bit of hex editor related stuff, I think I guess Wireshark is more network related, but you do see some hex there as well. So hex editors are basically computer programs that allow you to manipulate binary data and view binary data that constitutes as a computer file. So typical computer files occupy multiple areas of the disk, and then the contents are combined to form the file. There are two sections that you could see in the hex editor. One is the hexadecimal side, and the other is the character representation. As you can see in the image, the left is all the hexadecimal information, and the right is sort of the translated characters for that. Hex editors are designed to parse and edit sector data from physical segments of either hard disk or floppy disks, if anyone still uses those. And they're sometimes even called sector editors or disk editors. They're used to see raw data and exact contents of the file and be able to compare them. And hopefully we'll be looking more into that on Friday. Okay, so last we have network analysis. We did a Wireshark workshop a while ago. And if you were present at that, you'll be pretty familiar with how network analysis works. With tools like Wireshark, you could record network traffic. And usually you do this by inserting a PCAP or packet capture file, which is information about different packets that were sent or caught over the air. And with that, if you basically plug it into Wireshark or any other packet capture tool, you could filter packets by their protocol, source IP, and other information from that packet as well. So it's very useful for not only wireless stuff, but generally any networking that you could see, because it's not also just wireless, it's any network related activity on your computer. So yeah. On the right will be is information about the SSL handshake. This is something that you'll see pretty common. So when either two computers, a client and a server, share a or want to share information, you want to the design is to make sure that they're sharing data in an encrypted manner. So in order to do that, they share a common key or secret, which usually is there's different algorithms for encryption, but for the SSL handshake, the client sends a list of available cipher suites labeled as like client random and a set of bytes. The server also does that with server random. And with that, the client is able to create a sort of like a master key and then send it back to the server. And from there, the server and client then create a master key together in their kind of like own space. So because they share different pieces of information with each other, they're able to use that information to create a key. And there's depending on the algorithm you use for encryption, there's a lot of different ways you could do that. But ultimately, when you're doing different handshakes with um, in a network, there's going to be a common key that the two computers are using to decrypt and encrypt information. We won't talk too much about that, but that's the general idea of it. And you could see these different packets that are sent across for that using a network analysis tool. Okay. All right. So lastly, I think before we end it off, I think today's meeting will be a bit more shorter, but for again on Friday, we'll be deep diving into a couple more forensics tools, along with next week with Matt's memory or mobile forensics activities. So a couple popular instruments that you use for digital forensics include forensic disk controllers, which enable investigators to read data from a device without preventing it from being modified, corrupted, or erased. You also have hard drive duplicators, which also, as it kind of says, you could copy data from different hard drives or memory cards to a clean drive for analysis. And then finally, you also have password recovery devices, which can crack password protected storage devices using either machine learning algorithms or other password cracking algorithms that exist. I think a small aspect of forensics is that sometimes you'll have devices that are locked, and in order to access them, you need to crack the password. So password cracking is used a lot in forensics as well. A couple specific example or tools that are used in the field include SleuthKit, OS Forensic, FTK Imager, Hex Editor Neo, and Bulk Extractor. We'll go over the links in a bit, but SleuthKit is a file system and disk image analysis tool. OS Forensic is a tool for collecting and managing digital evidence across multiple file formats and storage devices. FTK Imager creates exact copies of drives and storage kits. Hex Editor Neo is a hex editor for low-level data inspection. And Bulk Extractor is able to scan disk images or files to extract to specific data. And just to like click on the links here, uh, these links have more different tools, or has a list of tools. I want to say that on next week we'll be looking at the Autopsy, which is also open source software digital forensic tool. Yes, you see FTK. And if you Google up common tools, you'll be able to find a whole bunch of tools that are listed. There's a whole bunch of ones, and there's also like volatility as well. So there's a lot of different ones that exist. I think this one is also similar with a whole bunch of tools as well. So TCP dump, Splunk, a lot of different tools for a lot of different reasons, but uh, each one has their own purpose and their specific niche. So that's pretty much it. We're going to end it off pretty short here, but again, on Friday, we'll be kind of going a bit more deep dive into forensics and what it has to offer and how to be able to actively use these tools. So I'm going to go ahead and stop the recording there. Okay. Let's see.